everybody, welcome back. This is Unit 3, Lesson 6, and we're in Section 7 in our notes on nuclear chemistry. And what we have to talk about in this section is really what makes nuclear reactions different from the rearrangement of atoms and ordinary chemical reactions. So here's an idea that I want you to just think about. Let's imagine that we had a proton. And we know that protons weigh 1 AMU. And we had a neutron. And neutrons also weigh, for those of you playing along at home, 1 AMU. If we were to put them together, pretend that's an arrow. If we were to put them together to make the nucleus with 1 proton and 1 neutron in it, what would you expect it to weigh? Okay, think about what you know in math. What would you think the mass of that whole would equal? You would think it equals the sum of its parts, right? You would expect it to weigh 2 AMUs. But the reality is it doesn't weigh 2 AMUs. The reality is that it weighs slightly less than 2 AMUs. It depends, but let's say it weighs 1.99018 AMUs. The idea is that it is slightly less. And you have to be able to answer the question why. And Albert Einstein is the guy that came up with this idea, is that when the nucleus is formed, some of the mass is converted to energy. So in making this nucleus, some of the mass gets shot out as energy. And that mass is traveling or that amount of mass that's converted, as you can see, is a really, really small amount. But since it's traveling at the speed of light, it's a tremendous amount of energy. So Einstein came up with this equation that relates the mass that's lost to energy. C is the speed of light. It's 3 times 10 to the 8th. And you have to square that number. And so even if the mass is very, very small here, you're multiplying it by a huge number, which is resulting in a huge amount of energy. So ordinary chemical reactions don't involve making the nucleus. Only nuclear reactions, that's why they're called that, involve making the nucleus, okay? So a nuclear reaction is different from a chemical reaction because in nuclear reactions, some mass is released as energy, and a little bit of mass makes a ton of energy. 3 billion times more energy than an ordinary chemical reaction. So mass defect is the mass that is lost as energy. And what we know is the greater this is, the more stable the resulting nucleus. So the greater the mass lost, the more stable the resulting nucleus. And the reason for that is the energy that's lost is equal to the energy that you have to put back in to break apart the nucleus. So binding energy is the energy you must put in to break apart the nucleus. And so if more energy is released, more energy has to go back in to break that nucleus apart. So the bottom line, probably the most important thing that you know happens in a nuclear reaction, but not in an ordinary chemical reaction, is that mass is converted to energy. And so I don't know if you remember, but we learned in our very first unit a law of conservation of mass. We said mass cannot be created nor destroyed. That's wrong. It can be destroyed. It can be converted into energy. And so that law has been revised to say that mass and energy, the total amount of mass and energy, can't be created nor destroyed. Okay? Because now we know this. So it had to be revised after Einstein's contributions to nuclear chemistry. There are two major types of mass converted to energy reactions. One is called fusion with a U, fusion, make sure you're saying it right and spelling it right. And the other is called fission with two S's. So fusion with the U, fission with two S's. Those are the two major types of nuclear reactions, and we'll learn more about those in our video tomorrow. Have a great night, everybody. Bye-bye.